Hello everyone. Welcome back to our mathematics classroom. Let me ask you something interesting. Have you ever thought about how a business decides the best way to invest money when resources are limited? Let's take our old friend, the furniture dealer. He has 50,000 rupees to invest and storage space for only 60 items. He can buy tables and chairs. A table costs 2,500 rupees and gives him a profit of 250 rupees. A chair costs 500 rupees and gives him a profit of 75 rupees. Now, imagine, if he buys only tables, he can purchase 20 tables, since 50,000 divided by 2,500 equals 20. That gives him a total profit of 5,000 rupees. If he buys only chairs, he can purchase 60 chairs, giving him a profit of 60 multiplied by 75, that is 4,500 rupees. But what if he mixes his choices? Say, 10 tables and 50 chairs. That would yield 10 into 250 plus 50 into 75, which equals 6,250 rupees. So clearly, the profit depends on how he divides his investment. And that brings us to the question, what is the best combination to maximize profit? To answer this, we need a mathematical approach. And that's exactly what linear programming does. Let's now express this problem in mathematical language. Let x represent the number of tables and y represent the number of chairs. Since we can't have a negative number of items, both x and y must be greater than or equal to 0. That's written as x greater than or equal to 0 and y greater than or equal to 0. These are our non-negative constraints. Now, there are two main conditions that limit the dealer. First, the total investment cannot exceed 50,000 rupees. Mathematically, that's written as 2,500x plus 500y less than or equal to 50,000. We can simplify this by dividing each term by 500, giving 5x plus y less than or equal to 100. Second, he can store only 60 items, so x plus y less than or equal to 60. These are the two linear constraints that describe the limits of his problem. Now comes the main goal, profit. We define a profit function, or what we call the objective function. Z equals 250x plus 75y. This function tells us how much profit Z he earns based on how many tables and chairs he buys. So the complete mathematical model becomes maximize Z equals 250x plus 75y, subject to 5x plus y less than or equal to 100, x plus y less than or equal to 60, and x comma y greater than or equal to 0. This type of problem, where we optimize, that is, maximize or minimize, a linear function under given linear constraints is called a linear programming problem, or LPP for short. Before we go deeper, let's clearly understand the structure of a linear programming problem. The objective function is the linear function z equals ax plus by, which we aim to either maximize or minimize. Here, a and b are constants representing coefficients such as profit or cost per item. The variables x and y are called decision variables because they represent choices we can control, like how many tables and chairs to buy. The constraints are the linear inequalities, like 5x plus y less than or equal to 100 or x plus y less than or equal to 60. They represent limits such as money or space. And finally, we always include non-negativity restrictions, x greater than or equal to 0, y greater than or equal to 0, because negative items or resources don't make sense. So in short, linear programming is all about balancing the objective function with the constraints to find the best possible outcome. Now that we have the equations, let's visualize the solution. If we plot each constraint, 5x plus y equals 100, x plus y equals 60, x equals 0, and y equals 0, we get a region on the graph where all these conditions overlap. This overlapping area is called the feasible region. It represents all possible combinations of tables and chairs that satisfy every condition. Every point inside this region, and on its boundary, is a feasible solution. Any point outside is infeasible, meaning it violates one or more constraints. Our goal is to find the point in this feasible region that gives the maximum profit, that is, the maximum value of z. Here's an interesting fact. In linear programming, the optimal solution always occurs at a corner point of the feasible region. Let's see how this applies to our dealer problem. The corner points of the feasible region are O at 0, 0, A at 20, 0, B at 10, 50, and C at 0, 60. Now let's evaluate the objective function. Z equals 250x plus 75y at each of these points. At point O, 0, 0, Z equals 0. At point A, 20, 0, Z equals 5000. At point C, 0, 60, Z equals 4500. And at point B, 10, 50, Z equals 6250. So, the maximum profit occurs at the point 10, 50. That means the dealer should buy 10 tables and 50 chairs to earn the highest possible profit. This powerful idea that the maximum or minimum value of a linear function always lies at a corner point is the very foundation of linear programming. So let's summarize what we learned today. Linear programming is a way to translate real-life decision problems into mathematical form. We first identify the decision variables, then set up the objective function, and finally include all constraints and non-negativity conditions. By plotting these, we find the feasible region, and the optimal solution occurs at one of its corner points. This method helps businesses and industries plan investments, allocate resources, or minimize costs efficiently. I hope now you understand how linear programming problems are formulated and why they're so useful in real-world optimization. In the next video, we'll explore how to solve linear programming problems graphically using the corner point method. See you there.